Welcome back to another video, and actually this video it's going to end our discussion of number systems and codes. Take a look at this picture. What I have here is something that you're probably very familiar with. You're not used to looking at it the way I'm showing it to you here, but this is called a 7-segment display. A 7-segment display. What this does is it will display the symbols 0 through 9. So what you have here, you have LED. A LED is a light emitting diode. So you have these little LED lights, and they're not round like most lights. These are like elongated. They're rectangular. So this is a tiny little rectangular LED light. I got one. These are all marked A, B, C. They're marked A through F, G, right? And right here, that DP, that stands for decimal point. That is a round LED light. But the idea is that each of these segments, a 7-segment display, so there's 7 segments or 7 LEDs. Each of these segments, you can be thought of as being connected to a switch. So I have this segment A, I have a wire going out over to this switch, and I got power here. So I might have some kind of power here. Actually, power is here. So this thing is, we talked about sources and sinks before in another slide. Here's a good example. If this is the device I'm talking about, here's a good example of current coming from my power source into the device. So this will act as a sink. So current will come from the power. VCC is always power. And current is going to flow down into the device, so it's going to sink. If you think of a sink like a drain, water drains out this way. So the source would be the faucet, the sink would be like the drain hole. This is a current sink, will come out if I close the switch, and it'll flow over here to ground. But to get back on track here, each one of these segments, these little LED segments, is connected through a resistor to a switch. So if I close switch A, segment A is going to light. If I close switch B, segment B is going to light. So I have a choice. I can control which LED over here lights up. Well, think about this. If I close A, B, C, D, E, and F, then that's going to make the symbol 0. That's going to make a 0. If I close A, B, G, F, C, and maybe D, that'll make, see, these are lit up, and that'll make a 9. If I close all of these switches, leaving the decimal point open, we won't have a decimal point. If I close A through G, it's going to make 8, the symbol 8, or the digit 8. So with this 7-segment display, I can display the numerical symbols 0 through 9. And I have the option of a decimal point if I want it. So you've seen this a lot, or variations of this. Your cell phone uses not a LED, it uses something called a LCD, a liquid crystal display. Pretty much the same thing. You have these segments you can light up, but with the LCD, because of the nature of it, the way it's designed, it pulls very, very little power when compared to a LED. But you want to make sure you understand how a basic 7-segment display works, because when you're dealing with PLCs, if I want to display a symbol, more often than not, they'll have some kind of display board like this where you can display symbols 0 through 9, and in some cases you can display other symbols. So this is pretty easy to understand. So with this, I want to get into the video, the PowerPoint. So this PowerPoint is titled Number Systems and Codes, but remember in an earlier lecture we talked about numbers. There's binary numbers, and then there's binary codes. And the one major difference is binary numbers are always, they use what you might call place value, or we call position weighting. It's the same thing. A code doesn't necessarily use place value. A code, I can represent information or data using a number, a binary number, or a binary code. Well, that code can just be a sequence of bits. So maybe I represent a certain piece of data using a certain sequence of bits, and then the the data next to it, I want to represent that, I'll use another sequence of bits. So in this PowerPoint, we talk about several different codes. These are not particularly number systems, these are codes. Some of the codes will use place value, and you'll see that some of the codes will use just combinations of bits. So we'll get into that. The first one I want to talk about relates to that diagram of the LED, the 7-segment display that I showed right before the presentation here. BCD. BCD is very important, so make sure you remember BCD stands for binary coded decimal. Binary coded decimal. I'm not sure it's written out anywhere, but I will ask about this at some point. BCD stands for binary coded decimal. So look for that on the exam, or probably more likely a quiz. Binary coded decimal. So what does it do for us? What is the purpose of BCD? Well, here's a list of a couple bullet points, but there's others. BCD provides a mean of converting easily from decimal to binary. So I can go from decimal to binary. You mainly want to do that when you're dealing with 7-segment displays, or something called a thumb wheel. So you've already seen a 7-segment display. A thumb wheel is like if you've seen the old padlocks they used to use for the lockup of like a bicycle, and it has like a little wheel. You can set a combination. You can just move a little wheel. It's like a little gear wheel. You can move to set the number 0 through 9 to open up like a padlock. That's what we mean by thumb wheel. Thumb wheel is you can actually just dial in a number. So that's a candidate for this, for BCD. So 7-segment displays and thumb wheels and devices like that would use or could use BCD, binary coded decimal. So BCD uses 4 bits to represent each decimal digit from 0 through 9. Mark this. This is important. Actually, the next slide that I'll show you deals with this. But this is the main thing here on this slide. I want you to remember that you got to use 4 bits to represent each decimal digit 0 through 9. This table will make it more clear. So here's the decimal number. We're going to count 0, and we only count up to 15. Let's say I have a 7-segment display I want to light up. And what I would use is BCD code. But the thing is that the 7-segment display, it only shows symbols 0 through 9. And so I can use in BCD binary 0 through 9. Look at that. I go 0, 1, and the number of bits increase. But if I want to represent that in BCD, I always got to use 4 bits. Not so much looking at the binary. Look more over here at this. I want to use 4 bits, four binary digits to represent each one of these. Now, where that becomes crystal clear is when I get down here and I have more than one and 1 decimal digit. So like right here, I have, let's look at this. I got a 1 and a 2. That's a 12. Well, to represent that 12, here is 12 in binary. In binary is a 1, 1, 0, 0. 8421 code. This is an 8. That's a 4. I get 12. But in BCD, you don't write it this way. You write it like this. I want to represent the 1 using 4 bits, and I want to represent the 2 using 4 bits. And that way, what I can do is, if I want to show, let's say I have a 7-segment display that counts from 0 to 99. So I would need 2 7-segment displays, because each 7-segment display can only display the symbols 0 through 9. So if I want to, let's say I want to be able to count from 0 through 100. I got 2 7-segment displays. One 7-segment display will display a 1, and the information to display that 1 will come from this. And the second 7-segment display will show the 2, and the information to light up to give the 2 will come from this. So for each decimal digit I need 4 bits of BCD code to express each decimal digit. So if I want to go all the way up to, let's say, beyond 99, if I have 3 LEDs, I'm going to need 3 groups of 4 bits for each one of those numbers. Once I get up to over 100 or 100 or over, I'll need 3 groups of 4. So BCD is pretty simple. Here's a decimal number, and the way I would show it, 7, I would show a 7, even though 7 is 1, 1, 1. If this is BCD code, you got to put that leading 0 there. It's got to be groups of 4. 8 is a 1, 0, 0, 0. Here, you could leave that 0 off and think, oh, 6 is a 1, 1, 0. But in BCD code, you got to put the 0 there. And so BCD is really simple if you understand the groupings of 4. So imagine this right here. This is actually my decimal number, but you can imagine that this is a 7-segment display where I have 1, 2, 3, 4 displays. So I can display numbers up to 9999. And to get to 7, now I'm going to think of the arrows going the other way. If this were a 7-segment display, then this BCD code will be fed to that display, and it will display the 7. This would display the 8, 6, and 3, and then that would light up 7,863. So this grouping of 4 is important. So you might use it on something like this, where you have a, well, remember I talked about the thumb wheel earlier. So maybe this is a thumb wheel where I can dial in these numbers. So I have a wheel that I can turn to dial in a 6, a 4, a 1, and a 9. Or maybe this is a keypad. I can hit the keypad 6, 4, 1, 9. Some kind of way I can input these decimal numbers here. Well, the decimal number, they're fed into the input module rack, but what I have to do is this has to go into this as BCD. It's got to be BCD, because the only way to show these numbers, to represent these numbers, and even my readout over here, I have a digital readout where I have a 7-segment display, but I have 1, 2, 3, 4 displays. It's got to be BCD. So notice inside the PLC, the signal processing, the processing that takes place. So I dial in this number, it's a decimal number. It's got to go in here as BCD. So in here I have, either in this device or this device, I got to have some circuitry that will convert that from decimal to BCD. And when that conversion is done, I get into the PLC, and I'm actually going to process the BCD. Even though the BCD is zeros and ones, I got to convert that to binary. So that's just a grouping it. I group it together as a binary code, but this has to understand that this is BCD and not regular binary, and it'll the circuitry to help it understand that. I process it, and then if I want to go to a 7-segment display, this digital readout, I got to go back from binary to BCD so that this understands. Okay, now I need four bits to represent each one of these of the 7-segment display and light it up. So here's a process, the whole process together. PLC processors function in binary, not BCD or decimal, so do not confuse the fact that this is zeros and ones. It is zeros and ones, and we use the binary digit zeros and ones, but it's not the same as binary. I can convert from binary to BCD and from BCD to binary. So BCD, binary coded decimal, that is one type of a code, and it actually uses position weighting. Here's another one though, gray code. Gray code. So gray code does not use position weighting. So here we have a type of code that just the sequence or position of bits will distinguish one code from another. Now what's important about gray code is that this one, progressing from one number to another, only changes one bit at a time. Now you might say, okay, what good is that? Well, I'll try to explain that in this next slide. But make sure on this one, these are good. Make sure you understand and read these. Does not use position weighting, so that's probably important. This is very important right here. This is this makes gray code really useful. Going from one number to another only changes one bit at a time, and then you can read the other two. But let's go over here and let's look at this. If you go in binary, and let's say we count, I go 0, 1, 2. I'm changing these bits as I go. I'm changing these bits. Well, you can really see it right here. If I go from this is a binary 7, this is a binary 8. If I'm counting in binary, once I hit this right here, if I go from a 7 to an 8, I gotta change all the bits. This 1 is a 0. Everything changes going from a 7 to an 8. Now the problem with that is, remember what we're doing. This is actually a really complicated process. I mean, I know you guys, you turn your cell phone on, you turn your laptop or your PC on, and you just expect it to work. Well, in order for your device to work, a lot of things have to happen. And not only does a lot of things have to happen, they got to happen at exactly the right time. So think about when you start your car, everything that has to happen. You turn that key switch, you got spark plugs firing at the right time, the cylinder's got to be in the right place, the right amount of gas and fuel. A lot of stuff has to happen. Well, multiply that by 1,000,000 when you're dealing with a computer or a cell phone. You got a lot of things going on. The heart of any system is, any digital system is the clock. We talked about clock circuits. So timing is a big, important thing when you deal with machines. The timing of when things happen and what happens. So it gets really complicated. More than we can talk about here. But the point is, every time I make a change in a bit, what you're really changing is a voltage. Remember we said that these zeros and ones, even though we're dealing with zeros and ones in binary, that really is an abstraction. That's for us as humans to understand. Machines really, even though we call it machine language, we call binary machine language, machines really only understand voltages. And the way we're doing it in this class, if I have 5 volts, that's going to represent a 1. If I have 0 volts, that's going to represent a binary 0. So I can actually represent a binary number with the presence or absence of a voltage, either 5 volts or 0 volts. We can even move it around because I can turn those zeros and ones into a pulse, a digital pulse, and we can move them around. We can move those bits around from one place to another because we understand that I have these things called shift registers. So I can have a number, a binary number, a voltage, and I can turn that voltage into a pulse, and I can move those zeros or ones around the circuitry in the digital device. Well, sometimes mistakes happen. You might have a binary number. You might have, say I don't know, this number right here, 0, 1, 0, 1. That's 0 volts. That's 5 volts, 0 volts, 5 volts, using the amplitudes that we talked about in this class. So anytime you change a voltage, there's always this chance that a mistake can happen. And how could that happen? Well, a lot of things can happen. One big thing with electrical components, electrical circuits, is what we call noise. Noise. Now, noise is not a sound. Noise in an electrical circuit is any voltage or current that exists in the circuit that shouldn't be there. So if you've ever been, well, I don't know if you guys even watch regular TV, but if you watch an old school TV set, sometimes you get, you might be watching TV set and your mom or your girlfriend or boyfriend, whoever, they turn on a mixer or vacuum cleaner and it puts these little lines in the picture. That's noise, and that noise might be coming through the house wiring, but it could also, if you have a motor that's running like a mixer or vacuum cleaner, anytime you have anything that creates an arc, it creates a radio wave that other circuits can pick up, and it can cause noise. It can cause unintended currents and voltages to appear in the circuit, that if you're watching TV, you could see a line that shouldn't be there. Or if you listen to the radio, you might hear static. Or if you're on your cell phone, it might you might hear fading in or out, or you might hear static. So it's really amazing that we can get any of this stuff to work. But here's the point, that the fewer things I have to change if I'm sending information, the less likely I am to make a mistake. So that's where gray code has an advantage. If I send information in binary, say I code it using binary. Well, if I code from from right here from a 7 to an 8, I got to flip all those bits. If I'm representing some, I don't know, some color or picture or sound using binary, if I code from a 7 to an 8, I got to change all 3 bits. Whereas if I use gray code, if you notice, as I progress down this list, only 1 bit changes at a time. So here, this bit changes. If you look, only 1 bit will change at a time. So for this reason, they call gray code error minimizing code. Let's look at this PowerPoint here. So you can look at this, mark it just to kind of remember it as you review it. Gray code does not use position weighting. Progressing from one number to another changes only 1 bit. Highlight this right here. That's the important part. Only 1 bit changes at a time. And you can read these other points. Now here's the point of gray code. So gray code is considered to be error minimizing because only 1 bit changes at a time. So if you have a need, we're talking PLCs here, but any digital device, if I was going to communicate, have devices communicate, and I want to minimize the possibility of making a error in a bit of information, a bit, a bit, then this would be one way I could handle it. I could use gray code. Now there's advantages and disadvantages to this, but the advantage of gray code is that it's error minimizing, and you're least likely to have a bit flip on you or to transmit the wrong information using gray code. Now there's another type of code that I want to talk about that's actually pretty important. This is called ASCII code. ASCII. And ASCII is actually, it stands for American Standard Code for Information Interchange. That's the ASCII. ASCII. And what this is any keyboard, like a computer keyboard, you have a keyboard in your cell phone, where you have, think about what you have on the keyboard. You got the alphabet, uppercase, A through Z. You got the alphabet, lowercase, A through Z. You have the numbers, the number 1, 2, 3, 4, up through 9, and then you have a 0. Now those are, even though it's the digits of 1 through 9, those are not numerical deals. That's actually a character. But the point is, you have all these symbols on your keyboard. You have the exclamation point. You have a star. You have a forward slash, backslash. You have a greater than, less sign. You have all these symbols on your keyboard. Well, remember, anything that goes into a machine has to be represented as zeros and ones. And so the letter A, or these special characters, it says you have 25 special characters like the @ sign, pound, and so forth. Anything on your keyboard, no matter what, has to be represented in binary as zeros and ones. And that's what this ASCII code does. So I'm going to pause this for a second and show you what that looks like. Okay, so I brought up this chart, and this is available on Canvas, so you have this already on the class website. But look at this. So what you have here is you have these codes. So for example, let's come over to here. All right, so let's look at this. So A, this is the uppercase A. Over here I have a lowercase a. Well, that A, when you press the letter A, uppercase A, or let's say lowercase a, you press that on your cell phone keyboard or on your computer keyboard, what goes into what's echoed to your screen is the A, either the lowercase or uppercase A. But what actually goes into the machine has to be zeros and ones. So this binary code right here, and this is 1, 2, 3, 4, 5, 6, 7, 8 bits. This is a byte. Remember we said most digital devices are byte oriented? That binary code represents A. That's the A. B is another binary code. C is another binary code. The uppercase A is another binary code. Look over here. I have the exclamation point, the pound sign, the dollar sign, %. All those special characters represented in binary. So the two most important columns here to understand is the actual ASCII symbol. That's the thing that you type, that you're typing out on the keyboard, and its binary representation. Now these other columns are, remember we said, well, who can remember like A? If I want to remember lowercase a, who's going to remember 0, 1, 1, 0, 0? You're not going to remember that. Well, you can remember that if I convert this to decimal, here it is. You might not be able to remember this sequence, but you can remember the decimal value 97. Or they also show it in hex and octal. So these other columns are just for us for convenience. But the important here is to know that every symbol has a binary representation. It's coded. There's a code that represents every symbol on the keyboard, uppercase, lowercase, and special characters. Now there's actually a lot of this digital stuff was invented in the United States. So you got this American, this A stands for American, blah, blah, blah. Well, what about other languages where they don't use these symbols, like Arabic or, God forbid, Mandarin Chinese? There's other languages. So there's actually a more universal coding system that they have. I think it's called Unicode. You guys can look that up if you want. It's been a while since I've thought about it. But this is usually, right now at least, for now, things are usually based in English for now, but there is that Unicode where they have other codes that basically Unicode takes all the languages, the major languages, and it will it'll do the same thing here. It'll give them a binary relationship. So look that up if you're interested in it. I want to get back to the PowerPoint now, and we'll continue our discussion on codes. Okay, let me get my screen fixed back right. Now, I just showed you the handout or the page on ASCII code, American Standard Code for Information Interchange. And so you can see how this is a good example of just the idea of coding something. So I can use binary, and here we actually use this regular binary to represent all the symbols on a standard keyboard. So ASCII code is important. I won't add, I may ask a question. You should know what it is, be familiar with that table, be able to use the table, have access to it. I could ask a question like on the exam. You want to have that table printed out at some point, but you don't have to memorize anything other than know what ASCII is and know how to use that table, how to cross-reference, say, if I want the binary for uppercase A or lowercase a, or for the hex value or whatever. Alright, so we're getting close to the end here. This next slide, I'm not going to ask anything about it. The point of this is that we've been talking about coding. If I can code something, then I can decode something. So this idea of encoding and decoding is important. And the purpose of this slide here is just to show you that there's actually chips or electrical circuits that do the coding, the encoding and decoding for us. So if I have something that I'm going to change into a code, I can encode something. So here's an example of an encoder. I have it says input decimal number, and I can output the same number but in binary. Then I've encoded it. Or I can decode it. It can go the other way. I can input a binary number and get out a decimal number. So it's actually these integrated circuits. IC stands for integrated circuits. They call it a chip because it looks like a little piece of, I don't know, I guess a little chip or something. I don't know. If you ever seen an IC chip. But the point is, you can actually, just like you can go out and buy a register, it's a physical thing you can hold in your hand. Even though we're considering a register and a word to be the same, thing. A register is actually a device you can go buy, install it, and use it if you know what you're doing. Well, you have encoders and decoders. You can do exactly the same thing. You can go out and buy an encoder or decoder, or usually you're going to buy both of those. And if you know what you're doing, you can design circuits where you can encode and decode information. Now, the rest of this I'm going to leave for you to read yourself. The rest of these slides. There is one thing I want to talk about. You can read this, and if you have any questions, ask, but it's pretty self-explanatory. But there's something else called parity that we need to we won't discuss it, because I can actually give you a homework on parity. So I think you're due for homework 3 or 4, so I think this is like homework 5 or 6. So I'm not going to talk about parity here. You can read this slide. You should read it, but you'll learn more about parity doing that homework assignment. There'll be some exercises that you'll go through, and it'll make parity, the idea of parity, pretty clear to you. It's a pretty good assignment. So with that, that ends this PowerPoint, and it also ends our discussion, our week 3 discussion on number systems and codes. So hopefully, guys, all that gives you some insight into the magic of these machines. In their world, they deal with zeros and ones. In our world, we abstract from that. We deal with numbers, usually base 10, but we can also deal with other bases like base 8 and base 16. Just remember, no matter what goes into a machine, no matter what, it's going to be converted into binary, into zeros and ones. So, guys, have a great rest of the day, and I'll see you soon.